start with a definition of Hess's law then, and it's one that you would find anywhere really. I'll read it to you first and then write it up. The total enthalpy change for a reaction is the same regardless of the route taken from reactants to products. Okay, so that's it's just a good starting point. So let's add that here. Right, the total enthalpy change for a reaction is the same regardless of the route taken from reactants to products. Now, part of the assignment actually asks you to explain the link between that and the first law of thermodynamics, so I'm not going to give the full explanation here, but it is about just conserving energy, really. That you can't lose it, you can't create it, so if you follow a route, ultimately you're going to be using the same amount of energy in the conversions that are there. So what I would just put, I'm going to put here, it's a consequence of. I'll put that in brackets because it is something that you will be able to look up quite easily. So the first law of thermodynamics. This word thermodynamics, I need to actually visit that at some point. I could have called this unit, I think, pretty much thermodynamics. It's not entirely, but a lot of it is sort of covered by that. So I'll talk about thermodynamics. I think once we've done the assessed content of this learning outcome, I'll talk a little bit more about that as a word and give you a bit broader sort of cover of chemistry, because it's yeah, it can be a bit misleading. I mean, its name tells you, thermo, heat, and then dynamic is movement. So it's about the movement of energy, but that's so much tied up with so much of chemistry that, yeah, you can be a bit misled by it sometimes. So I will be back to that word. Sometimes called the law of conservation of energy. Alright, so what we're doing really is just finding a route that's viable, perhaps, a route that is possible at normal temperatures and pressures very often. I'll give you an example. I'll try not to give you the example that you're actually going to use next week, or I could do. Well, yeah, why not? You're going to look at two reactions, one involving sodium hydrogen carbonate and another one involving sodium carbonate, in order to work out the energy that would be needed to convert sodium hydrogen carbonate into sodium carbonate. Now, you would do that by heating it up. But if I gave you some sodium hydrogen carbonate, I think I've got this right, I need to check the assignment actually. If I gave you some sodium hydrogen carbonate and said, right, heat that up and measure the heat you've put into it, well, you can't, can you? You could put some in a dish, put a Bunsen burner under it, but there's no way you could measure the amount of heat energy you'd put into it. But you can take a roundabout route, and by moving equations around, switching them back to front and multiplying or dividing them, you can actually get the enthalpy change in an indirect way. So it's a way of making an indirect calculation of something, and it's very useful. So the way it actually works out, if you think about the energy diagrams that we've met before with endothermic and exothermic reactions, the idea then, so it's used to work out just thinking, we've got a couple of people missing, so I need to be thorough on this. Enthalpy changes which can't be measured directly, practically, or both, which okay, so if you can't do it in a practical way, then what we've got, if we used an energy diagram approach, and this was sort of what we were looking at earlier, when we originally introduced the idea of endothermic and exothermic. If you're trying to go from, let's say, reactants to products, in terms of energy, okay, what sort of reaction is that going to be? The energy change that we've got here, the delta, yes, it's exothermic, because our delta H, all right, is negative because we're losing energy, aren't we? So energy lost. I've not left enough space over that side now. So if we've got a situation like that where our reactants lose energy in order to become the products, then we don't just have to take that direct route. We could actually have any number of intermediates. If we have our reactants and products in the same positions, and I should have started further to the left here, that's always my issue. So reactants there, products there, we can use an intermediate, or we could have several intermediates. Let's put our intermediate up here. So we could take a different route to get. We can still get from our reactants to our products using the intermediate. No, well, a catalyst can actually provide intermediate options, but no, this would just be a completely separate reaction that we could go from our reactants to the intermediate first. So we could go from there where our delta H would actually be positive. All right, so that's part of the delta H. And then we could go from our intermediate to our products. And we've still got there, haven't we? We've taken a different route. But if this is our delta H that we want to work out, let's make it a little bit clearer. All right, if we want to know that, let's call that delta H1. And we'll give the others some identities as well. The little one there from reactants to intermediates, I'm going to call that delta H2. And the one from intermediate to products will be delta H3. If you can, in a lab, carry out delta H2, or you can measure delta H2 and you can measure delta H3, how would you work out delta H1? Yeah, which from which? Yeah, 2 from 3, 3 minus 2. So what you've got there is a way of calculating delta H1 is simply delta H3, okay, which is of course going to be negative like delta H1 minus the delta H2. All right. And this is what you're going to do. We're going to do a lot of mathematical examples of this, and then you're going to do the practical version of it. It's not always going to work out exactly in terms of molar quantities and stuff like that. So sometimes you have to multiply through. Sometimes you end up with fractional molar quantities. That's fine. It's just manipulating equations to do a job for us, really. Now, what this means then is that we've just got two routes. If you can express that in a different sort of way, and you'll find in quite a lot of sources of information an approach that's a little bit different. And I think I mean, it's still a standard sort of approach, but it's not using an energy diagram. And the usual way that you'll see it is if you start with your reactants and you want to get to your products, so you'd usually think of it like that, as a sort of equation, if you like. Again, started a long way across, haven't I? Then, if this is our delta H1 that we want to actually measure, this is our route 1, if you like, to get from there to there. That's the obvious route. However, our intermediate can be down here, or intermediates, I don't know, doesn't really matter. And if we want to go from our reactants via the intermediates to the products, and we can have our delta H, I can't remember, it was 2 from there, wasn't it, and 3 over here. Then our alternative route, route 2, could be around there. Now you might have another option, which I realise this is going to throw things into confusion because I haven't got this in my own notes, so I could be messing things up. But what if in the lab you could do, whoops, right, as an alternative, if you've got your reactants turning into products being the one that you wanted, right, we'll still call that delta H1. And our intermediate option down here, right, it's a slight sidetrack. But what if it wasn't an intermediate between the reactants to the products directly? Let's say that you could convert your reactant into the intermediate. That'd be delta H2. But it's also possible for converting the products into the intermediate. They could sort of meet like that. All right. So this is a what if. Pardon? An example. It's not really an example. It's because of the ones that you can do in the lab. I suppose the one that you're going to use. So you can convert both sodium hydrogen carbonate and sodium carbonate into sodium chloride, carbon dioxide and water. So what you're going to use will actually be like that, your sort of intermediate. All right, but you can do those two reactions in the lab. Well, the one that you can't do is sodium hydrogen carbonate into sodium carbonate. How are we going to, what's route 2 going to be then? How could you calculate delta H1 from this? Well, the energy change for a reaction is the same number, whichever way it goes, but you will remember back for endothermic, exothermic, you could reverse a reaction and all you do is change the sign. So the important thing that you could do here is that there is a potential reaction that goes that way. And what's its energy change? It's the minus version. So it's minus delta H3. Okay? It's the same reaction but in reverse. Well, either, an endothermic reaction, if you reverse it, will be exothermic, won't it? That's a really important idea that you're going to need, because sometimes you'll just need to reverse a measure, a number, a value. Yeah. So our route now to get from reactants to products is minus that. So it's the delta H2 minus delta H3. Or if you like, it's delta H2 plus minus delta H3. Because the route that we're taking now has gone, route 2 is now here. It's going that way. And to get there, you go the right way down that one, but you're going the wrong way up this arrow over here. And so all you do is reverse the sign. Okay, so depending on what reactions you're given, and it's a matter of just getting the right things on the right-hand side and right things on the left-hand side, and sometimes you'll need to turn them round. Right? I will show you how this works. Don't panic, this is early days. All right, let's give you one example on here, and then I will work through a few that I've got on the next slide, and then I'll give you some to play with as well. Right, let's start a new, oh right, hang on, let's start a plain one. Okay, first example then. Nitrogen dioxide, NO2, which is a gas, can be converted into nitrogen and oxygen. That's actually 2O2 there. Where does that happen? Nitrogen dioxide converted into nitrogen and oxygen. Converted into. Have you got in your cars in the exhaust system you have a catalytic converter, and that's one of the things it does, is convert nitrogen dioxide, which is toxic, pollutant, into nitrogen and oxygen. So your car can actually be producing oxygen. There you go. Just need to get it to photosynthesize and we'll be all right, won't we? So that is route one, all right? That's the thing that we want to actually work out. Now, I'm not just going to put one. This is an enthalpy change of reaction, and I'm going to give it, that's the one we're working out, but sometimes you can put a 1 next to that R just to make it clearer. We can, however, go via, this is an easy one, we can go via nitrogen oxide, right, rather than dioxide, NO rather than NO2, and oxygen. And not surprisingly, you can go from nitrogen oxide and oxygen, you can keep breaking it down to get to there. Now, in order to break nitrogen dioxide into nitrogen oxide, you have to put some energy in. So the delta H for this one, you see, that's the problem, is plus 114.4 kilojoules per mole. Now, one of the problems that you'll have in the assignment is how the heck do you lay things like this out? Drawing triangular layouts and getting all the information on. You'll find a way. It's one of those satisfying sort of things. For this reaction, however, for converting nitrogen oxide and oxygen into nitrogen and oxygen, that actually releases energy. So the delta H here is minus 180.8 kilojoules per mole. Now you can see why I would normally number these. So I'm just going to call this delta H naught R1, delta H naught R2, delta H naught R3. Doesn't matter whether that's an uppercase or lowercase r, usually. But we can now do something with them. So, route 2 is fairly obvious for this one. All right, route 1 is just the one that we got at the top. Okay, so if that's route 1, up there, but route 2 is going, I haven't really left myself enough space, let's put it in the middle. All right, that's route 2. From those two reactions that we know the enthalpy changes for, if if we follow the arrows in the direction they are going, then we only have to add up our contents, or our values there. So we are going from the nitrogen dioxide down, so it's going to be delta H naught R2, and then we continue from that to go up the other side. So we're just going to add the value over there. It just happens to be negative, of course, but that means that our delta H naught R1 is 114.4 plus, and it's often a good idea to actually keep putting the plus and minuses in here. Although I haven't put it for that, I know. But I'm going to put 180.8 with its minus sign in brackets so you can see where it came from. If I just put 114.4 minus 180.8, you don't necessarily get it, because what we're doing is adding those together. We're continuing that route round, which is, calculators at the ready. That sounds right to me. Minus 66.4 kilojoules per mole. All right, make sure you've got the units in there. All right, so overall this gives out heat. Okay. All right, yeah, there's usually a small reason for that. Now, sometimes it's not an obvious route because the things don't add up. What we've got there is nitrogen and oxygen on the left, nitrogen and oxygen on the right, nitrogen and oxygen down at the bottom. But sometimes it includes substances which you have to introduce them on the way up and down the arrows. But I'll show you some examples as we go along with that. I'll give you a second. Oh no, let's have a look at some of the examples that we've got now that I've put on the board, hopefully, on this next. Now, these will need moving about to use them. I'm sorry they will be a bit blurry because I just snipped and pasted from a PDF, just because I found lots of examples that were quite useful. So bear with me. I'm just going to move rather a lot of them. Let's just park them out of the way, and then I can move them as we need them, can't I? Right, this, is that big enough to read? Right, a bit woolly, I know, but we've got two reactions there. From the following enthalpy changes, calculate the value of delta H naught for this reaction. So we've been given two, and we're asked to do a third one. Now, that's not then so obvious as to what's happening. We're being asked to calculate for the reaction carbon plus oxygen makes carbon dioxide. So that's the one that we want. Hang on a minute, I'd worked all these out in advance so that we could do it with the diagrams, and then you hopefully reach a point where you don't actually need the diagrams. They're good for explaining what's happening, but sometimes, you know, it comes sooner rather than later, that you can look at the equations and think, well, to get that onto that side of what we want and that onto that side, we'll turn that one round, we'll divide that one by half. And what you end up with is something remarkably similar to simultaneous equations. So, you know, if you're all right at simultaneous equations, then this is a very, very similar approach. If you think about it, it is, isn't it? You know, you're putting together two reactions to make a third. You're almost solving. Yeah? You'll see. Right, where to start with this one? Well, we're being asked to work out, I'll do it in a colour so that it stands out from that, and we're being asked to work out carbon, solid, plus oxygen, gas, gives us carbon dioxide as a gas. Now, there are other ways of getting there, and it seems to be via another compound, which is monoxide, yes. So the other thing that we've got is carbon monoxide. So this is not going to look quite like the one I've just done, but our intermediate is going to be carbon monoxide. Never mind the oxygen in this particularly at the moment, because we can go from carbon, let's call that, well, this is going to be this is the one that we want to work out. Okay, I should have put that over there, sorry. Let's remove it from over here, it just gets messy. What we're being given, if this is our reaction number 1, and these are 2 and 3, whether they'll fit that way around, I'm not entirely sure yet. How are we going to get reaction 2 in there? Carbon and half a mole of oxygen will make carbon monoxide. Well, we know that when you burn stuff without enough oxygen, you get carbon monoxide. So carbon to carbon monoxide will actually be down there. And the reaction that gets carbon to carbon monoxide, we don't have to put the oxygen in there, has an enthalpy change of minus 110.5. Missed off the per mole for that. All right. Never mind the rest of down here either, and you're thinking, well, why? The oxygen is not the important bit here. How do we do the other bit? Carbon monoxide plus half a mole of oxygen gives us carbon dioxide. Oh, well, what do you know? Carbon monoxide to carbon dioxide goes up there. This time, we've got a reaction taking place. There, it's 283. Okay, we've got 2 exothermic reactions there. Not surprisingly, when you burn carbon to carbon dioxide, it is exothermic, isn't it? Now, you could put a reaction next to this. Reaction 2 is going on from here to here. It's just I haven't written it all in, and it doesn't matter. The actual molecules that are involved are not that important. But the common part to both of those is that. So that's got to be our intermediate, hasn't it? Okay, well, this is not exactly difficult, right? Because how do you get from carbon and oxygen to carbon dioxide? How are we going to get delta H naught R1? Just going to add them together, yeah. Okay, so that, I need to show you something else in a minute. Delta H naught R1 is R2 and, whoops, didn't leave enough space there, R3 added together. So we've got minus 110.5 plus minus 283, whoops, lost the 3, minus 283.0, which looks like 393.5. Yeah? Good. Minus 393.5 kilojoules per mole. What we've actually done is add the 2 reactions together, in a way. And just to prove, you know, that we don't need to actually put all the details in. And I'm going to have to move that bit out of the way in a minute. Right, if I come down a bit, this is going to get messy, isn't it? Oops, it's not going to let me do that until I extend the page. Sorry, just parking. I'm going to use an awkward one next, I think. Okay. If you use the simultaneous equations approach, and it sounds odd, but it works. If you add reactions, what have we called them? 2 and 3, haven't we? 2 and 3 together, all right, like simultaneous equations, and I mean literally like that. Carbon plus, and I'm not putting the state symbols in, I know it is a bit sloppy, but I just want it to be clear, so miss those out. Is that equation 2? I got that the right way around. Yes. And then equation 3 was carbon monoxide plus half an O2 gives us CO2. Okay. If you literally now add those together, add the lefts together and keep them on the left, add the rights together and keep them on the right. Okay. We've got, let's start with the top, we've got a carbon. We've got a carbon dioxide underneath it. We've got 2 halves. Well, what does that makes 1, obviously. So we've got a O2. And on the other side, we've got a carbon monoxide and a carbon dioxide. What's common to both sides? CO. That was our intermediate. Well, if you put some in and you get some out, it can come out. We can ignore that. Exactly. We are now left with C plus O2 gives us CO2. Right, this is, you know, there's no chemistry happening that does this. This is manipulating the information that we can get. And so that is now equation 1. All right? Magic, isn't it? Okay. I might do... I'll do an awkward one now. I really need to do an awkward one, don't I? Oh, a very awkward one. Right, on my list it is. Right, so there are others here that I'm just going to delete some of these because they are... Take that one out and take that one out. I'm going to use this one, but I think I'll cut it and put it onto the next page. Yeah, and I've got a lot to cover. However, I know I've got some spare time next week. Ooh, that's really blurry. Sorry. Right. Is that the one? Yeah, okay. So we're being asked to work out a reaction between hydrogen and fluorine. Not surprisingly, quite a strongly reactive combination. And you can see, you know, we've got 2 negative numbers there. So hydrogen, fluorine. Oh, sorry, that's not what we're working out. We're being given a reaction between hydrogen and fluorine, strongly exothermic, and then another one between hydrogen and oxygen, which is again exothermic. We're being asked to work out a reaction between fluorine and water. Now, this is not so obvious then. And the way I've written it in my notes isn't going to be terribly helpful. But we want to start with our 2F2. All right, so fluorine is a gas, plus water, in this case standard state liquid. I'm sorry, I'm going to remove that and do it slightly further to the right so I've got more space. Habit I need to get into. 2F2 and 2 water gives us 4 molecules of hydrogen fluoride, which is a gas, and some oxygen, also a gas. So that is our reaction. Let's flag it up. That's number 1. So this is going to be the one that we want to work out. Delta H naught R1. How are we going to get there? What have we got? Well, what we've got on the left, we've got fluorine and water. On the right, we've got hydrogen fluoride and oxygen. Now, the only one of these 2 equations that produces hydrogen fluoride is number 2. So we know that we're going to produce hydrogen fluoride down here. So let's, all right, well, let's put what else are we going to need? We're going to need the hydrogen's going to be the sort of common part of this. But if we go from hydrogen to hydrogen fluoride, H2, effectively it's plus F2 coming up here. All right, it's told us that that is a delta H of, which one are we going to call this then? Let's call that 2, obviously, is minus 542.2. We do have a bit of an issue with that though, don't we? Without multiplying up our reactants, how many hydrogen fluorides are produced in equation 2? There's only 2. All right, so, yeah, well, we have to consider, do we double it, do we half it, all that sort of thing is going to come up. But yes, we're going to need to double it, basically. So we'll have to double that value to get up there. So yes, we have to go up it twice, if you like. The other information that we've got, hydrogen and oxygen can combine to make water. Well, the water is there, so it makes it sort of slightly wonky, but I'm going to do it like that. All right, so plus oxygen would take us to water there. And so we've got a value for that. Our delta H naught R3 for that is minus 571.6 kilojoules per mole. So how are we going to work out delta H naught R1 for this? Where are we going to start? It's not immediately obvious, is it? Because both of the arrows are coming towards our equation. All right, but how about, you know, if we want to, let's say we start, right, hang on, we want to get from here to here. So this is our starting point. So our first journey is down here, isn't it? So we're going to have to, for the first bit, we're going to have to reverse that as our first job, aren't we? And then in order to get 4 of those, that's right, we're going to need to multiply that by 2. All right, those are where we want to get to. So this actually becomes easier to do without the diagram. Because you start, it's sometimes better to do it the simultaneous equations way and say, how can we get the right number of items on each side? A word that's often used for this process, actually turning this round or reversing it, is flip. You flip that one, right? You flip the sign. I think I'm not going to be doing enthalpy change of formation today. Sorry. Okay, so delta H naught R1 is the reverse, so it's minus the first bit of our journey is actually R3, isn't it? Right? You know, these will not come immediately, so don't think, oh, I've got to get this now. You need to, I'm going to give you examples to do. That's the next job, right? So that you can try and work them out. If you can do them without drawing the diagram, that would be good. But we'll see. They're useful because they show your understanding of the route. But then, yeah, we're going to need 2 lots of yeah, so 2 of those. So our overall change will be is minus this minus number here, 571.6 plus 2 lots of minus 542.2. So that works out at 571.6 minus 1084.4, I think. I haven't actually worked that one out. So, yeah, if anybody wants to check that one, you can. This is done just using 2 equations. I'm going to give you some that involve 3. They call it stretch and challenge. I know you had a hard morning on the kidney anyway, so this is, yeah, a bit beyond, isn't it? But oh, sorry, yeah. All right. Just check my calculations on there because I'm well known for arithmetical errors. So what we're looking at about minus 512.8, is it? Minus 512.8 kJ mole minus 1. Okay. Well, what is the easy way? Standard form. Simultaneous equations. Simultaneous equation approach to this. Sort of. Yeah. What you've got to do is to look at the equation you're trying to make and the ones that you're given. So you're looking at the answer and thinking, how can I manipulate those equations that I'm given to make that last one? So if I'm going to write them down sort of simultaneous equation style, and then I'll have to edit them, all right? So it'll be we'll have to do things with them. Right, I'm going to have to scroll down and rewrite them because we've lost them off the top there. And I don't know what I've done with them. Lost the actual example sheet that I had, never mind. I'll go back to, nope. All right. We had, right, let's come back up here then. We're trying to make 2F2 and 2H2O into, right, so we want as our end product, let's use another colour so it stands out. We want to get 2 F2s plus 2 H2Os to turn into 4 HFs, again leaving all the state symbols out for now. How many O2s? Was it a single one? Okay. All right. Now, let's just look at the 2 equations we were given. I'm going to have to keep scrolling up and down here. So if we scroll back up, let's have a look at equation 2. Whoops, equation 2. Equation 2 has hydrogen on the left, fluorine on the left, and hydrogen fluoride on the right. Now, if we look at our end equation, the really important thing there is getting that hydrogen fluoride on the right. So we can leave that equation, equation 2, we can leave it that way round. And we know that from the diagram we've just drawn. All right, but, have another look, go back up. H2 and F2 gives you 2 HFs. Well, if you double that, all right, 2 lots of equation 2 would give you 2, what came first? Was it the F2? The H2s first, is it? 2 H2s plus 2 F2s gives you 4 HFs. At that point, we've got that. We've also got that, in a way, but yeah, we might not get there immediately. I'm probably going to have a third line in here to have to cancel some things out. So just doubling that is a good start. The other equation, if we look at equation 3, here, H2 plus O2 gives us 2 H2Os. Right, okay. H2 and O2, 2 H2 and O2 gives us 2 H2Os. Well, our H2O is on the left. So we need to flip that one to get H2 on the left. So it was Let's use another colour for that one. Our product had to be over here, so that was two H2Os, wasn't it? So this is, and I'm going to use the word flip because it's short. If we've turned it round, we could break that now into two H2s and an O2. Okay, now we can cancel this out because we've got two H2Os, we've got our O2, we've got a bit of extra, however. So if I put another line in and add them, we get 2H2 plus 2F2 plus 2H2O will give us 4HFs, 2H2s and an O2. But the common thing on each side is 2H2. So if you put them in and you get them out, they didn't do anything. So we can get rid of that because it's going in and coming out, so it's not involved in the reaction as such. And so we're left with our final product. All right? We're not doing practical today, no. Yeah, I was hoping we'd have done this bit by now, but we can't leave it and move on to the next bit yet. So I'm going to give you some examples. I'm going to give you a worksheet to have a go at. It does come with answers on the back. But what I would very strongly suggest is working together on this. And I don't think the answers are actually... Oh, yes, they are on the back. So I managed to print me spare sheets as well. So I think we'll put this on pause.